So if I want to guess what happens in this system, if I start coupling out the atoms resonant at one particular point, I can kind of guess straight from this diagram. Basically, if I have a bunch of atoms trapped in here, what they're going to start to do is as they hit that coupling surface, they're going to start coupling out. So I'm going to get some atoms out there, and then I'm going to get some atoms out here, and so on and so forth. I can kind of imagine what's going to happen to these atoms. These atoms are going to slosh backwards and forwards, and eventually they're going to hit that coupling surface, and they're going to come out. These atoms are going to fly off and never be seen again. These atoms are going to roll down that hill, or maybe if they come out over this side, they're going to roll down that hill and never be seen again. These atoms are going to never be seen again. And so what I kind of expect naively is that all those atoms are going to slowly leak out. So let's see what actually happens when I use this semi-classical model here to model the system and find out what happens to the total density as a function of time. Now we can use physical parameters for our couplings and our traps and so forth, and so the natural length scale tends to be something like micrometers and the natural time scale tends to be something like milliseconds. And you can see that what happens is the total density seems to stay roughly in the trap for large periods of time. In fact, it's just oscillating backwards and forwards. Not very simply, you can see that there are these extra flicks here, so there's a little bit of structure and complicated behavior going on. We also do see some atoms simply falling out under gravity. So that kind of falling there is quadratic, so that's just falling out under gravity. And so that's a little bit surprising. We do have some atoms falling and leaving, but most of the atoms appear to be staying. Why is that? And this is not a function of this nonlinear term, which can certainly complicate things, but even if we turn that term off, even if there's no interaction between the atoms at all, we'll still get this behavior. Well, as you may have reverse engineered from the title of this lecture and the title at the top of this slide here, the correct way to think about this is to start thinking about the dress states. And if we want to look at the dress states, then the dress states are just those particular states which are actually eigenstates of this system. So what are the eigenstates of this system? Well, let's start with the simple case first. If we don't have any interactions, the case we know immediately pretty much is the case where we also don't have any of these coupling terms. So if the coupling is off, if we're not coupling these different levels, then they're all completely independent. And with a diagonal Hamiltonian, what we have essentially is 5 Schrodinger equations that are completely independent of each other, and so we have 5 eigenvalue problems that work the normal way. And if this trapping potential is harmonic, then we know the harmonic oscillator eigenstates, and so we just have harmonic Gaussians in here, and so on. For the weaker harmonic trap, we would have similar solutions that were just a bit broader. Now for the linear potential, the eigenstates have a continuous index rather than a discrete one because they're not bound, and they're airy functions in fact, and we know what the waves will do, they'll just fly on down the hill. And similarly for the anti-trapped potentials, we'll just have eigenstates that have continuous indices, and what the waves will do, of course, is that they will flee the center of that trap. So those are the bare states where we're ignoring the coupling between the different levels. What about the dress states where we include those couplings? Now in general that's a difficult problem, but we can make it quite a lot simpler by looking for what's called the quasi potentials. So in component form our Schrodinger equation looks like this, where these VJKs are just the components of this big matrix here which has the potentials and the coupling in it. Now the quasi potential idea is that we're going to work in the basis that diagonalizes this matrix here. So it's not actually the eigenstates of the system, we're just going to work in the basis that locally diagonalizes that matrix. And that's going to give us a spatially dependent diagonalization. And so the basis that diagonalizes that is going to have 5 components and is otherwise going to be a function of x. And so what we're going to have is we're going to have a linear combination of the different components of the MF states for each x. In the absence of any coupling between the states, in other words, when that omega for the coupling term is 0, then the eigenstates are simply the MF states. In the presence of that omega, what we're going to get is we're going to get 5 different eigenvalues. So instead of the 5 potentials, we're going to get 5 different eigenvalues. The potentials themselves are very simple. They're just the gravitational potential, which is linear, added to the trapping potential, which is simply a function times the MF state. Now when we diagonalize this, we're going to get a particular linear combination which will give us our local eigenstates. We'll also get local eigenvalues of the following form. So the reason that's so simple is that we haven't solved the full eigenvalue problem, we've just solved the eigenvalue problem for the potential matrix itself. But it does provide a perfectly viable basis for the system, and that basis is carefully chosen to make that part of the Schrodinger equation diagonal. Now if these coefficients don't change too much, then in fact they're not going to be affected very much by that gradient term either. So if we rewrite the Schrodinger equation in this new basis, we're going to get some terms that look very, very familiar. where these functions psi are just linear combinations of the old functions phi, but we've chosen those linear combinations carefully so that the Schrodinger equation that we get, this is an approximate Schrodinger equation, but it is approximately equal to a Schrodinger equation that is completely independent for each different component. So instead of having 5 coupled partial differential equations, we have 5 independent partial differential equations that look just like a normal Schrodinger equation, except they have this different potential, and these are called the quasi potentials. And when the interaction is off, if we look at the interaction picture, we're going to get potentials that look like this. But when we turn the interactions on, we're going to find our eigenvalues split, particularly at these couplings here. So at these points where we're on resonance, we're going to find that in the presence of the interactions, that those eigenvalues are not going to be all identical. And so instead we're going to have quasi-potentials that look like this. And so these things are not exactly dress states, but they're very close to it. And so we know roughly just from looking at those quasi-potentials what particles put in those states would do. And so in this first two states here, obviously they're going to be trapped. If we put them in the middle, then they're obviously going to spread out and do some fairly complicated oscillatory behavior, but they're going to stay in a regime and they don't go too far away. Particles in this potential, you see they're still untrapped, they will fall just as before. Particles in these bottom two quasi-potentials are going to be a little bit more interesting. If they're placed in the middle here, they'll essentially be trapped. They'll be metastable. They'll have some tendency to leak out to the sides, but in general they'll stay pretty much as placed. And this is true for this one as well. So they have a kind of metastable place they can be in the middle. In the very long term, however, they'll leak out. So actually, if you put particles in this middle part here, and they're in a superposition of all those different dress states, then nearly all of them are going to stay around. We'll have some oscillating wildly, we'll have some oscillating a little bit, and some falling out. And of course, if we look at the model, that's exactly what it was showing us. We have some particles oscillating, some fairly complicated particles. We can imagine those are probably the particles in those dress states there. And we have some particles falling out under gravity. That's presumably things that were in those modes there. And so in fact, the tendency for those things to stay there, for the atoms to stay trapped when you've got nice strong coupling, is again much clearer if you look at the dress states. Sometimes it's nearly impossible to predict the correct behavior of physical systems when thinking about things in the bare state basis. So for example, if we look at these couplings in the bare state basis, you might say, look, I just don't understand how we can couple between these states and end up not eventually having our atoms fall out of the trap. And indeed, for weak couplings, that's true. So for weak couplings, we slowly leak out at these things, we eventually trickle down here, and the atoms are gone. In the dress state basis, what that looks like is that these transition points here, the energy gaps between them are quite small, so it's very easy to make transitions between them. And even if we start largely up in this state, we will eventually, which means we'd be starting in this upper state here, we eventually leak out. When the coupling is really strong, then these energy gaps increase and the dress states become a more reasonable basis to think about things in, and we see the kind of behavior that we saw here. But in fact, that behavior was so unexpected from the bare state point of view that there were people at ANU that didn't believe it. Our simulations were showing it. We had a lot of doubt. Is this really what's going on? So of course we did the obvious thing, which is to try the experiment. And in the experiment, we slowly turned up the strength of the coupling and saw how many atoms eventually got out of the trap. And so here we have the number of atoms left in the trap versus the strength of the coupling. And we see, of course, if we have, for a fixed amount of time that we're coupling the atoms, if we have the coupling strength very low, then the atoms start in the trap and they stay in the trap because the coupling hasn't had time to do anything yet. But then as we turn up the coupling strength, the atoms rapidly fall out of the trap over time. And they go down and down and down. And then, of course, as we turn up the strength of the coupling further and further, we eventually start to get into this dress state regime where the atoms are going to be bound, and indeed we see that the number of atoms stuck in the trap goes up again. And so this is experimental data showing the dress state picture actually works. It really explains why there's this shutdown of atomic flux in atom lasers when you try and drive them too hard.